So welcome to our video, and what we're going to be talking about is the exponential function. Our equation that we got was f of x to x. So we start by making a table, and in order to find the coordinates to plot our, and we start by -3, -2, -1, 0, 1, 2, and 3. We're going to be plugging each of the x values into the equation. So we start f of x equals 2, -3. So because there's a negative value, we switch the 2 and it turns into 1 over 2. 1 over 2 times 1 over 2 times 1 over 2, which equals 1/8. So we didn't want to make them into a decimal, because that's not the actual way to do it. We're leaving them as a fraction. So -2 will equal 1/4, and -1 will be 1 over 2. Then 0 will start 1, 1 will be 2, 2 will be 4, and 3 will be 8. Okay, so now that we have our table done, we're going to start graphing it. We're going to start plugging them in. So we're going to start with 1/8, which is -1/8, which is really not really touching the x-axis. Then we go to 1/4. Then we go to 1 over 2. Then we go to 1. Then 2. Then 4. And finally 3. So as you can see, it's gonna give a J shape, which is what an exponential function will do. So next up, we're going to be talking about the x-intercept and the y-intercept. So we have our graph that we showed previously, and what we discovered was that for the x-intercept, there was none. But why is that? How do you know that there's no points that plug into the x-intercept? So let me explain. So as you can see in the graph the arrow that I'm showing, there is no points that are touching the x-axis. They're actually above the x-axis, which means that there is no intercept. So in the y-intercept, in this case, there's only one coordinate that touches the y-axis, which is 0, 1. So as you can see, and we'll be showing you right now, is that point that the arrow is pointing at, that's where it's actually pointing into the y-intercept. So once again, if you put none for x or y intercepts, that is because they never cross y or x axis.
If there are any possible maximums or minimums, may it be relative or absolute on the graph. And so far, we have come to the conclusion of no, because of the example I'm about to show you right now. In a moment, I will show you the information I have gathered. So as you can see, there is no possible maximum or minimums, because a maximum is the highest point in a graph and the minimum is the lowest point in a graph. And since this part keeps on going to the negative side of the graph, it's never gonna fully stop. And so is this one. It just keeps on going to the positive side.
So we now move on to our domain and range. So once again, we'll show you the graph. Remember this, the domain is, we're going to be focusing on the x values. Once again, the domain will be focused on the x values. So for the range, on the other hand, is the y values. Once again, the range is y values. So in our equation, the domain is parentheses -infinity and +infinity, end of parentheses. The range is bracket 0 to negative. Remember, what parentheses means is that number after the parentheses will not be included. As to the brackets, the number after the brackets means that that number is included in this equation. So we were able to determine the domain by, as you can see in the graph right now, where the arrow is pointing at in the negative side, it will always have like a negative number. It will never stop. That's like the main point. So that's why we kept it as negative infinity. And as it goes, it starts from negative infinity and it will go up to positive infinity. So that's kind of basically the domain. As to the range, on the other hand, we start at the coordinate 0 and 1. Start at 0, and then from 0 it goes to positive infinity.
Behavior, because it's a J-shaped graph, it keeps going up and up forever. So when f of x is 0, then x is negative infinity. So that means it keeps going on and on and on. So the f of x, the y, which is f of x line here, it stops when it keeps going. When the end is at 0, the x is at negative infinity. And when f of x is at infinity, then the x is at positive infinity. So they're both positive infinity, and they both keep going forever positive. But for the end behavior, it stops at 0 over here. But over here, as you can see, it keeps going positive. So for the interval infinity, we have the increasing interval over here. And but it's not so much and there isn't a decreasing interval, because once it hits 0, as it shows here in the end behavior, the interval stops. So it never hits down here, and so it never really decreases. It just keeps going up because it is a J shape. And because it's a J shape, it keeps going up, and it never ever keeps going down. It may, like, the arrow may be here, but once it hits 0, it stops. It doesn't keep going down. So therefore, it is an increase. It is an increased interval. Never negative and always positive, because it doesn't go down here. It never goes down here. As I said earlier, it only goes to 0 and then stops. So therefore, it is only a positive interval. So it is both positive and
of
increasing.
this equation is going to be f of x equals log 2 then to x. And the way I got this was because our original equation was f of x equals 2 to the power of x. And by simply just rewriting this, we can make it into this equation. And I will demonstrate on how you do that. So can I rewrite the equation here to x? Then I'm going to label my parts A, B, C. And then to do this, it's going to be f of x equals log, this part is going to be A. Then this part is going to be B. And then this big number right here is going to be C. So it's going to be log of 2, and then with x. And that is our inverse. A real world example we chose as a group was a group based on germs and how fast they multiply. The problem states that we have to find the growth rate of germs between 1 to 4 hours. And the information it gives us is that germs multiply into 2 daughter cells in 15 minutes. We need to calculate the total germs at the end of each cycle to get the total germs at the end of 4 hours. So we, at 0 hours, meaning what we start off with, we get 2 parent germs. My bad. Then after a full hour, we get, so during that 1 hour, we have 2 parent germs, and for each 15 minutes, we get 2 new daughter cells. So for the first 15 we have now four germ cells. Then for the next 15, which is going to be 30 minutes, we get 4 times 2 equals, we get 8 germ cells. Then for the next 15, which is 45, we get 16 germ cells. Then for the last 15, which is going to be 60, we get 32 germ cells. And as you can see, from 2 to 32 germ cells in 1 hour is a pretty big number. And then that's just for the first hour. To get to the 4 hours, I need to multiply 32. I need to multiply 32 to 4 times. No, my bad. We do this whole section all over again. So, as I'm going to demonstrate on this graph, I'm going to show how this real-world example is implicated into our lives. I mean, how it's a real-world example of the exponential function. So for 15 minutes, I'm going to put it at 4, and for half of that hour, it's going to be at 8, and then at 45, it's going to be at 60 here, and then 60 at a complete hour, it's going to be at 32. As you can see, our graph is already going to be exponential right here, and it's just going to continue up and up and up. Because right here we have that one, and that one.